Okay, hi everyone. So today I'll be going through church numerals in Source Academy. I'll be going through how one can first arrive at an expression for increment repeater. Then I'll be going through how one can analyze the time complexity and understand intuitively what decrement repeater does. That's quite interesting. And after that, where we see that decrement repeater in this case is actually O of n. So one would actually seek out a better way to implement decrement repeater to achieve O of 1. But it turns out we actually need to redefine the church numerals in a certain way. And so the rest of it will be motivating the derivation for um, the derivation for that set of church numerals. So we'll arrive at the following new definition of church numerals, and one would see that we will need to re-implement what we had already, which is increment repeater and add repeaters for this new definition of church numerals, which shouldn't be too hard because we can kind of refer to our previous implementation with a bit of caveat that we need to adapt it to the new definitions. And then lastly, we implement decrement repeater in O1 as the grand finale. So without further ado, let's jump right into it. So first of all, what is church numerals, right? So this thing called church numerals is basically a way of representing numbers in natural numbers in functional programming without any in a very abstract way, without any like actual data. So usually if you represent 2 in the computer, it'll be represented as 1 0 in binary, right? um, but in this case, that's not what we're trying to do over here. In this case, we're actually trying to represent 2 with the with a with an abstraction, right? With an abstraction that with a lambda that takes in a function f and some data x and applies f on x twice, right? So that's the whole idea, that twice the function, the church numeral 2, right, representing 2 in functional programming isn't data itself, right? It's actually a lambda abstraction, right? Abstraction just means that it takes in something, right, and then it does something else. So that's what we call a lambda abstraction. Is the number 2 is actually a lambda abstraction that that takes in some function f and x, and it describes the behavior of f being applied on x 2 times, right? So you can kind of think of it as like the saying that the identity of some guy over here is the identity of this 2 is defined by how he treats others, right? So like someone's, without being too um, without being too metaphorical, someone's character is defined by how they treat others, right? So in that parallel, right, the twice function, the 2 church numeral, is defined by how it treats functions that are passed in. So without further ado, let's go through some like quick examples just to introduce the idea of church numerals. So forgive me for being a bit pedantic, you can kind of skip ahead if this is too simple. But if I call the twice function on, let's say, the add 1, right, the increment function, and I pass in 5, right, then one would expect that this calls add 1 of 5, and this increments 5 twice, so it'll be add 1 of 6, which will give me 7. Right, and just for another example, let's say I call twice of square of, let's say, 3, right? One would expect that this is square of 3, and this will give me square of 9, and this will give me 81. Alright, so so this is basically how this is twice applied on various function f. We can see that there's no restriction. The definition of twice doesn't restrict what function I pass in, right? It could be as general as you want. Some generic function f, and in this case I'm passing in these functions and some data, right, any data, and it applies that function f on that data twice. Right, so of course in this case in this example I'm using like real numbers, but the idea is that as much as possible, besides this example, the idea of 2 is just that it's applying a function f twice. Right, so turns out we can actually do quite a lot with this. You can get quite far. You can define addition, you can define multiplication, you can define exponentials, you can define you can define quite a lot of things from here, right? So we'll be going through some of the basic arithmetic operations that you can define using church numerals. Yeah. So let's see. So we see that in this case we want our first task is to implement increment repeater such that tries is we can get tries from increment repeater of twice, right? So this increment repeater is a +1 function of sorts, but instead of working on numbers like numerical data, it applies on functions like church numerals itself, the abstract notion of 2 in this case. So how do we achieve such a thing, right? So I think it helps if one kind of sketches out what they want, right, from the function. So it always helps to go with a concrete example. So if we want increment of twice to give you tries, right, we need to think first, how do we get out this tries thing, right? So we see that we want tries to be a function that takes in f and x, and it applies f on x 3 times, right? So what that would mean is that we want this is basically the definition of tries, right? And we want to define increment repeater in such a way that we can get this right hand side, right, when all we have access to is twice. And so the first thought over here would be, wait, that's kind of impossible, right? How do we, if increment repeater only has access to twice, how do we get the f, right? How do we get the f that we want? And the answer to that is to always add a lambda abstraction, right? So we see that currently increment repeater takes in a number, which I'll call, let's say, n, right? And okay, let's call it number, right? So and right now we can't really do much with just number alone, right? But what we can realize is that increment repeater of twice, it returns you tries, but tries itself this thing itself, the thing that we're trying to return itself over here, is a function, right? It's a function that takes in f and then x and then applies f on x 3 times. So what I'm trying to say over here is that if we do not have enough information to produce this body over here, we can always add a lambda abstraction, right? So we can take in a function f in this case, right? Take a lambda abstraction over functions f that we pass in to tries, and in this case there's no harm doing x as well, right? And what do we see? We need this to be f of x, right? And so we might be tempted to do something like that, right? But realize that this will work for increment repeater of twice, but it will not work for a general increment repeater of n, right? Some generic number n, right? So the pattern over here we observe is that when I have tries of f of x, right, this actually equals to the inner part over here, right? The inner part over here is actually twice of f of x, right? How we can see? So we can see it the following way. We can see it this way, right? Twice of f of x is this thing, and twice of f of x is just f of twice of f of x, right? So generalizing this, right? Generalizing this idea, we can realize that to increment a repeater, we have access to a number f and x. What we can do is we can call the outer f, right, f on number and f of x, right? So this is our increment repeater, right? Just following this pattern over here, we see that so one can arrive at the following expression by kind of writing out what we have access to, right, which is twice, and realizing it's this form, writing out what we want, which is tries, which is of this form, and by noticing the pattern that, hey, actually thrice is just f applied on this part, which is just what we have, right? We have access to number, right? We have access to twice. Then doing the following substitution, we can generalize it as follows. So if I call increment repeater on, let's say, a number like 2, this gives me a number 3, right? So this entire thing is thrice, right? And it's thrice, and we can check that it is in fact thrice, because thrice takes in the function f, takes in the x, and it applies f on x 3 times, right? And we can generate that behavior using the twice function and the f, right? So that's basically increment repeater. And I think if you get this whole idea of, if you get increment repeater, you kind of get the essence of church numerals already. So the whole idea is that church numerals are defined by precisely how they behave, right, when you pass in a function f and how many times that f is being applied on the data. Alright, so we can go ahead and run this. You can see that for the first one of alert, which is thrice of display, we see that it appears 3 times, right? It appears 3 times here, and then 4 times on display, displays it 4 times, right? And the last time is simply the return value, so you don't really need to care about the last one. The white one doesn't really matter, right? So yeah, so let's move on to the next section, which is when we define the zero repeater, and the decrement repeater, right? So we've done increment repeater. The question now is, how do we do decrement repeater? And it turns out it's actually quite a lot harder, right? But thankfully the question, in this case, we are given the form of decrement repeater, and we are simply told to explain the time complexity, and it will also help if we kind of understand what's going on, right? So I'm going to go ahead and delete the following, maybe just leaving the increment repeater around, and we see that over here we have zero repeater, which is this, right? So it takes in f, it takes in the data x, and it applies f on x a total of 0 times, right? So that's that, right? So that's kind of intuitive. It takes in f, and then it simply returns the identity function. So decrement repeater is this monstrous thing which I'll go through in a short while, but we can see that twice is f applied on x twice, and thrice is the increment repeater of twice. But what we can do from thrice is we can decrement it one more time to get back twice, right? So question is, how do we undo one application of f, right? It may seem kind of challenging, and in fact it is, because there isn't really a way to undo function applications, right? If you think about it, once you feed the function some data, once you've applied the function, there isn't really a mathematical operation that undoes it, right? Things like inverse functions aside, because we're talking about we're talking about abstract functions in this case. There's no notion of an inverse function, right? So how do we do this? So it turns out the trick is quite clever. So let's try to analyze this the following way. So we see that decrement repeater, this is monstrous expression, but at the core, right, it seems to be doing something with the 0, 0 repeater, right? So there's a pair of zeros over here, which I'll just denote as 0 and 0. So just note that this, even though I'm writing the numerical zeros, I actually mean church numerals, right? So church numerals of 0, which is a 0 repeater. I'm just writing it 0, 0 so that it's easier to follow. Okay, so this is this part of it. If we take a look at the following part here, what do we see? We see that this function, right, it takes in a pair p, and what does it return? It returns another pair, right? And what does that pair contain? It contains the tail of p as well as the increment repeater of tail of p, right? So basically, if I were to write down what that function does abstractly, it takes in a pair xy, right? And what does it map to? It maps to y and increment of y, right? So this means that if it takes in 0, 0, can we see what it maps it to? So I'll call this function increment pair. we see that increment pair maps 0, 0 to 0, 1, right? So increment pair applied once, right? Yeah, and what happens if you apply it again? Right? If you apply it again, right, you see that increment pair would take the second parameter and move it to the first place, and then you take the second parameter and increment it by 1. And that's what we see, right? So if you continue this another time, right, we see that this will be 2 and 3. And so over here we can start to see a pattern, right? So we see that this is once, right? This is the first application, this is the second application, and this is the third application. For that, we can see that if we continue this pattern, for the nth application, right, we actually get n minus 1 and n, right? So if we apply it n times, the nth application of increment pair on 0, 0 will give you n minus 1 and n. And what do we see over here? We see that if I have a church numeral n, right, what that gives me the ability to is to apply a arbitrary function f on an arbitrary data x, which I can choose. And in this case, we have just, by analyzing the following increment pair function and realizing that when I increment 0, 0 n times, it gives me n minus 1 and n, we see that this actually gives us a very convenient way to get n minus 1 from n, right? Isn't this clever? So like, if we look at decrement repeater, right, now we will see that it takes in a repeater, which is basically n, which I can call n, and this n gives me the ability to apply any function I want on any data I want. And in this case, I choose the function to be increment pair and the data to be the church numeral 0, 0. And what do I see at the end of it? At the end of it, I get n minus 1 and n. And so all that's left to do is to extract out the n minus 1 by taking the head of this pair, right, the first element of this pair. So we see that decrement repeater takes in a repeater, and what does it do? It applies the following function, right, this increment pair function, repeater number of times, right, n number of times, right, and what does it apply that on, right? It applies it on the 0, 0 pair, and at the end of it, this entire thing will give you the n minus 1 n pair, and then I extract the head to get you n minus 1. So I hope that this kind of clarifies what this monstrous expression does. Is the idea is actually really simple, right? It's just this at work. So yeah, isn't that kind of elegant? So okay, so now we can try to analyze the time complexity of this, right? So the time complexity of this is going to be O of n, and the reason is because if I take in the number n, right, I want to, and I apply increment pair n number of times, what it gives me is, if I apply increment pair n number of times, each time I do increment pair, the time complexity is O1, right, because this is O1. So if I apply it n times, the total time complexity of decrement repeater will be On, where n is the repeater. Okay, so this is cool, right? We have analyzed the time complexity of decrement repeater and understood how it works, and most of the next discussion will be driven by how we can improve this On time complexity to O1. It turns out we cannot do this easily, right? Because there's no I don't think there's a way to do this easily. I don't think there's a way to do it at all without modification to the definition of church numerals. So that's what's going to kind of follow from here. And we can see how we can achieve decrement repeater in O1. Yeah. So before we move on to decrement repeater, it's worth kind of discussing add repeaters as a side, because this is one of the primitive operations that we also want to do with church numerals, right? And in this case, Yeah, so in this case, the expression over here, we may think we want repeaters of, let's say, twice and thrice, to give me 5, right? 5 times. And how I can test so is I can apply it on display, and let's say display high, right? So I would expect that this prints high 5 times. Yeah, 5 times in orange, right? And so how do I implement this add repeaters? So I can implement this add repeaters in the following way. So one can observe that um, if I do 2 plus 3, what does it semantically mean, right? Semantically, we can arrive at 5 in the following way, right? We can say that this is simply 3 plus 1 plus 1. So we do plus 1 2 times, right? And more generally, if I do n plus m, right? How I can get the result is I can get it by incrementing m n number of times, right? So I do this n number of times in total. And so if I had to write it out like this, I want to say this is increment repeater of increment repeater many times. And the last time, after repeater 1 number of times, I want to pass in repeater 2, right? And we see that this is where we can use repeater 1, right? Because there's no way to, there's no dot isn't a valid like expression in source, right? We want to encode the idea of incrementing the repeater 1 number of times, and we can do so by using repeater 1, right? Because repeater 1 has the ability that you can pass in any function and any data, and it'll apply that function on the data and repeater 1 number of times, right? So that's precisely what we're going to do, right? We're going to take repeater 1, and we're going to pass in increment repeater as the function f, right? As this function f over here, right? So this is my f, and the repeater 2 is my x, right? It's the data, and what is it gonna return? It's gonna return the f applied on the x repeater 1 number of times, right? And that's precisely n plus m. So you can see that this works over here. It's 5 times, and we are very happy. So that's great, right? So I think this brings us to the discussion of going back to decrement repeater. How do we implement decrement repeater in O1? Okay, so from here, it's worth looking at this definition and trying to understand why we define it this way, right? So it turns out that in order to achieve decrement repeater in O1, we need to redefine our church numerals in a way that the 3 repeater has very easy access to the 2 repeater. Right, so what does that mean? So we want the 3 repeater to be able to access the 2 repeater easily, but we see that there's a bit of a problem, right? A 3 repeater is defined by its behavior when you pass in an f and x, right? So how can I capture a reference of sorts? How can I capture how can I capture a reference to this 2 repeater if it doesn't appear in the parameters, right? So the whole idea is that maybe I can modify the definition of church numerals a little bit. So instead of a 3 repeater being defined as taking an f and an x and applying f on x 3 times, what if I'm a little bit cheeky and I instead of applying f on x 3 times, I actually pass in to f the 2 repeater, right? So remember, the reason why we make this design decision at this point is because this seems like one of the only ways I can kind of capture the idea of the 2 repeater, right? This is one of the only ways where I can preserve some preserve the 2 repeater in the definition of the 3 repeater, right? If I do not do this and I do as before, right? So the previous definition, we see that increment repeater, what increment repeater does, it takes a number. What does it? It takes a number and then f and an x, and it simply applies f on a number and f of x. You see that number in this case is kind of lost, right? Because I'm applying number on f of x, and number itself is gone, right? Like I do not have a, if I get 2 from 3, I no longer have a reference to 2 anymore, right? 2 is being applied on f and x, right? And after that, after you use a function, it's gone, right? So that's kind of why we want this definition where the previous repeater, the previous number, is preserved in its raw form, right? In its raw form like that, so that I can easily retrieve it and do whatever I want with it later. In the case of decrement repeater, that would be just returning this guy, right? So yeah, so that's the whole motivation for why we want to pass in the 2 repeater into our function f, even though it complicates the required function signature, required f by quite a bit, right? And the reason is because I need to preserve a copy of this 2 repeater, because over here when I use the 2 repeater, I do not have reference to it anymore, right? So that's one point, right? That's why we pass in the previous number to this f. Another point to make over here would be, why am I passing in an empty lambda in this case? Like why this doesn't seem useful, right? And in this case, the reason for doing so is known as lazy evaluation, right? So the reason why we do this is actually for time complexity purposes. So later on you'll see that when we reach the final form for a decrement repeater, in order for the time complexity to still be O1, right, which was the whole purpose of this fruitful exercise, right? In order for the time complexity to still be O1, I need this to be lazy, right? If I do not make it lazy, then what happens is that upon passing in my function f, right, in Source Academy by default, the arguments, you learn this later in the later chapters, but when I pass in, you learn this in the meta circular interpreter chapter, but when I pass in arguments into a function, they need to be evaluated first, right? And the only way I can avoid an evaluation is if I have a lambda abstraction like this, right? So this delays the evaluation of this function body over here. So that's what this is for, is to maintain the time complexity. Okay, so what do we see over here? We see 0 repeater is the same as the before, right? It takes in the function f and the x and applies f on x 0 times. Then what is 1 repeater? 1 repeater takes in f and x and applies f not on x 1 time, but it applies f on the pair, right? It applies f on the pair where we pass in the 0 repeater, which is the previous repeater, as well as this lazy function, right? And so looking at this pattern over here, we can see that increment repeater should take the following form, right? It should take in a repeater, and it should take in the repeater in this case. And remember previously what it looked like is we took in an f and an x, and previously, right, this was using the previous definition, this was simply f repeater f of x, right? But in this case, this will no longer work, right? Because this kind of breaks the pattern over here, which is 1, 2, and 3, right? Instead, we actually need to pass in repeater, which is the previous repeater, and then we need to pass in a lazy lambda, and that returns the following body, right, which is repeater of f of x. So this is just kind of replicating the behavior we see over here. So this makes sure that if I call increment repeater on 2 repeater, it gives me 3 repeater, right? Exactly as defined over here. So it makes it consistent. So this is our church numerals now, And working with this definition, we seek to implement add repeaters again, right? And we can try to use the same definition, but we'll soon see that we run into a bit of an issue, which can be resolved with a bit of a modification of the f that we pass in. So what do we want to try over here? So let's try naively to call increment repeater like this, passing in repeater 2, right? So this was what we did previously, and this worked previously, right? This seemed to work fine just a while ago. By the way, see here, when we try to run this, so 2 integers simply takes in a repeater, and there's some magic over here. You can just trust that it does its job and prints the number. Otherwise, you see over here, we see that running this, we see that line 6 has a problem. Yeah, there's some expected 1 argument but got 2. So what's happening over here is that what's happening over here is actually a bit apparent if we try to expand the following thing out. So we see that we're calling add repeaters on 2 repeater and 3 repeater, right? And what does this evaluate to? This actually evaluates to substituting in the definition we have, the candidate definition we have over here. We actually see the problem, right? We see that this evaluates to 2 repeater on increment repeater and 3 repeater, right? And so we go another layer of unwrapping, substitution. And what do we see over here? We see that this gives me, so increment repeater is the f, and the data in this case is the x, right? 3 repeater is the x. And so what do I see? I see that this gives me basically this entire function body, right? This entire function body. So this increment repeater passing in 1 repeater, and this thing, and then this f is increment repeater, and x is 3 repeater, right? So yeah, so what do we see over here? We see the problem immediately, right? We see the increment repeater is something that takes in a repeater and an f and an x, right? But what are we passing it in here? Over here, we're actually passing into increment repeater a pair, right? We're actually passing in a pair of 1 repeater and a lazy lambda, right? So yeah, so we see the problem over here. We see that the f that we passed in over here is not a good candidate, is not a good f, right? The f that we passed in here is actually bad because we expect that the f, right, in this case repeater 1 being one of these repeaters, right, we expect that the f that we pass in can accept 2 arguments, right, a pair of arguments. But in this case, the f that we passed in is just increment repeater which doesn't take a pair, right? So what that tells us is that we need to change. The idea is still more or less the same, right? The idea for repeater 1 and incrementing repeater 2, repeater 1 number of times is still the same, but we need to modify our f to adapt to this new church numerals definition, where the f that we pass in actually needs to take in 2 arguments. And this may seem kind of tedious, but this will actually come in, the same idea will come in useful later when you choose an f to have decrement repeater done very easily. Alright, so yeah, so in this case, I'm gonna call increment repeater wrapped increment repeater. So this wrapped increment repeater, I'm gonna define it up here, and the idea is that I want this wrapped increment repeater to wrap the behavior of increment repeater, except that it can accept the function signature of having 2 arguments passed in, right? So that tells me that this actually takes in a pair, right? So now when I pass in wrap increment repeater over here, this will be wrap increment repeater, this will be changed, and this will be changed, right? So I want wrap increment repeater to emulate the behavior of increment repeater, meaning that I don't really remember, semantically I want the same thing. It's just I need to adapt to this new signature, and how I can do so is by considering what it looks like, right? So I want 2 repeater to be 2 repeater of wrap increment repeater of this, to kind of semantically be increment repeater of one repeater of wrapped increment repeater of 3 repeater, right? So we see that we want we want the following expression, right? We want this line, line 21, to evaluate to line 22, right? And if we stare at this hard enough, we see that we want line 21 to evaluate to line 22. What parts of it is repeated, right? So this wrap increment repeater takes in the previous number, as well as I'll name this entire thing, I'll name it lazy, right? And lazy for lazy evaluation. And I want this to evaluate to the following expression. And so we can see that I want wrap increment repeater to evaluate to increment repeater of this thing, right? And what is this thing? This thing is the body of the lazy function, right? We can see that this highlighted part is this highlighted part, which is the body of the lazy function. And so that means that I actually want this to be increment repeater of lazy, but not lazy alone, but lazy evaluated, right, on the empty parameter set, right? So yeah, so actually staring at this and writing down what I want for this to evaluate into leads me to this expression, and this is actually the correct expression. So if we comment this out and run it, we can see that this is in fact 5, right? We have successfully re-implemented add repeaters and increment repeater using by adapted to the new definition for church numerals. Okay, so yeah, so if you understood all this so far, the remaining part will actually be quite simple. All that's left to do is to implement decrement repeater, but turns out, unlike the previous definition, the ON definition, where you increment a pair n times and you take the head out of it, it turns out the definition for decrement repeater in this case is actually quite simple. So good news for us. So I want decrement repeater of 3 repeater to give me 2 repeater, right? So let's think about how we can do this. So remember just now I said that 3 repeater, the definition of 3 repeater has now been adapted to have 2 repeater, right, in the definition. And how I can access the 2 repeater is through this function f, right? So I believe the important observation in this case is to realize that is to first write it out, right? So write out what I want, right? You should always write out you should always try to expand the requirements that you want. So I want decrement repeater of 3 repeater. What do I want it to be? I want it to be 2 repeater. Alright, I want it to be 2 repeater. And how can I access 2 repeater, right? So we can see that if I pass in 3 repeater, what do I have access to? I have access to this entire function, right? I have access to this entire thing. So I want decrement repeater to take in the 3 repeater and make some amount of manipulation, some amount of probing, something, right? So some operations on this entire expression, right? And I want the operations here to extract out 2 repeater, right? I actually want the operations here to extract out the 2 repeater. And so now the question is, what can I do, right, on this entire monstrous 3 repeater expression? And the answer in this case is there's not much I can do with a lambda except to apply it, right? Apply it on passing in some parameters, right? In this case, the key observation in this case is that what I can do with this thing is limited, but yet the potential is endless, right? In that I can only apply this thing on some function f, but at the same time I can choose whatever function f I want. And so the idea is that if I choose a clever enough f, right? If I choose a clever enough f and a clever enough x, I can actually extract out the 2 repeater, right? So in this case, I want my repeater to I want to pass in a clever f, right? I want to pass in a clever f, and then I want to pass in a clever x, right? Some choice of x. I can choose whatever I want for this clever f and clever x, but if I choose it correctly and well enough, then I can actually extract out the 2 repeater from this entire thing, right? And so if we look at the body over here, what is the clever f that we actually want, right? So I'm going to define these as constants, clever f and clever x. What are these clever f and clever x for that I want? For now, clever x can be anything I want, right? I'm just going to name it 1, 2, 3. It turns out this will be important for the base case later, but more on that later. So let's look at clever f for now. Right? I want clever f to extract out the 2 repeater in this case. And if we look at what f does, f takes in, we can first look at the function signature, right? F takes in the previous number as well as lazy lambda, right? And what do I want f to do? I want f to extract out the previous number, right? I want this entire thing to give me 2 repeater. So in this case, it's actually as simple as just extracting out the first element of this pair and leaving lazy completely alone, right? And yeah, and actually that's basically it, right? So if I run this, you see that this actually works, right? So I encourage you to kind of replay this part a little bit, and the best way to learn this is to try to explain to a friend, because when you explain things, you really clarify your understanding. And so yeah, so this is actually all there is to it, right? So before we go, right, there's just one more edge case that we need to consider, and that is the clever x in this case. So we try this on 2 repeater, this works as well. It gives you 1. If we try it on 1 repeater, it works as well, it gives you 0. But if we try on 0 repeater, remember we want decrement of 0 repeater. We want decrement of 0 repeater to give you the 0 repeater, right? But if you run this, it sees that we get an error, right? So the reason is because if we expand decrement repeater around the 0 repeater, what we see is that this actually evaluates to 0 repeater applied on the clever f, right? Applied on the clever x. And what does that give you? That gives you 0 repeater of clever f and clever x gives you clever x, right? Because we apply clever f on clever x 0 number of times. And so we actually want this clever x to be the 0 repeater, right? And if I close this, that's precisely what we have. And we can check that the 2 repeater still works, and yeah, and all the other numbers still work. So yeah, this is quite an interesting problem. We have managed to achieve decrement repeater in 01 time, and it's actually just this, right? So of course I can inline it by just substituting it in, but I think leaving it in this form makes it clearer. So yeah, I hope you enjoyed this intellectual exercise, and let me know what other videos you want me to make. And yeah, hope this helped. See you next time.